Welcome to this lecture number 6 on illumination engineering. This lecture is titled Photometry. Recall that we mentioned in the last class that in order to understand anything, it is necessary to be able to speak in terms of certain quantitative numbers. That is to say, any quantity that needs to be assessed, we have to hang a number. In fact, measurement becomes a very important issue, and anything when you want to measure, it is necessary that you should be able to have reproducible measurement issues. So that all this calls for having a standard, and this is done by way of having standardization, which we saw in the last class. So what do we do in this today's class is essentially, having learned what is a standard unit of light adapted for illumination purposes, we need to measure some of these things for our other sources, and this branch is what we call photometry. And in fact, the objectives of this lecture listed are: 1. To be able to understand what is a photometric bench, what is an illumination meter, understand the light distribution curves, what is a Roseau diagram, and what is a luminaire. So this is the framework under which we are going to address this particular lecture. Repeat that we are looking at measurement aspects. Understanding of no subject is complete unless we are able to measure and express it in numbers. This is in fact based on a quotation by the Lord Kelvin. Now, in a last class we did look at what should be a primary standard as far as this goes, which went through series of changes beginning with the wax candle and pentane lamp. Finally, the primary standard was adapted as a good radiator whose is maintained at the freezing temperature of platinum. Having looked at the standard, the immediate thing was to talk in terms of units in which we are going to express these radiation, because there is no point in measuring and giving a number if we are not able to express it in certain units. And that is how we have defined the light output from any of these sources in terms of the original candle. That is how the term candela has come, is the luminous intensity, and the total flux which comes out of a source, assuming it is a sort of a point source, was given out as 1 I. If I is the luminous intensity, I over 4 pi lumen. Lumen was the unit of light flux, and since most sources to begin with were based on what we know today as incandescent lamps, which can be approximated by point sources. So they based on the light flux available in all 4 directions. As we said, it can be viewed as a point source. So at radially away from the source, the light flux is going to be of the similar level, effect of the light. So that is expressed as mean spherical luminous intensity, and the effect of this light on any test object is talked in terms of illuminance per unit area, that is lumens per unit area, which is expressed in lux. Recall in the last lecture on laws of illumination we defined this. Now all natural things follow some form of a inverse square law. Same thing holds good for light also. That is what we saw. We had illuminance inverse square law, and now supposing the light the test object vis-a-vis the light are inclined, then we also saw, in order to arrive at the illuminance, the Lambert's cosine law comes into picture. So this is illuminance is the effect of this light on the test object or the object that is being perceived or viewed Just as you have in an electric field intensity at any point, which is the effect of the system of charges that are available to us. And how do we measure? That is where the issue is. In fact, I said right in the beginning of this lecture that we need to measure, we need to give some number so that we understand the phenomena a little more, and any measurement would call for having a standard, and that's what we saw in the last class, and that was a good radiator or a black body maintained at freezing temperature of platinum. Now, the easiest way to measure would be to have a comparison with a standard. That is how one could do. Now, the issue is very simple. We do not we do not use the primary standard for all measurements. In fact, primary standards are maintained in the standards laboratories. So, we do not have we have lamps compared with the primary standard, which can be viewed as secondary standards. Like for any other measurements, let us look at our measurement of length, weight or voltage or current. We have standard meters maintained in the standard laboratories, and secondaries are substandard meters used for our laboratory calibration at the. So, similar way we have the incandescent lamp is used, it is compared with the primary standard and is used as a laboratory standard. The test source is compared with the laboratory standard, and this process of comparing and measuring is what we call as the photometry. In fact, how do we define the light or radiation ability of a source? In terms of the luminous intensity, and it is categorized, or the unit of luminous intensity is candela. So, we do this, and one has to keep in mind that this lamp, which is compared with the primary standard, we have to take care by not to be used beyond 50 to 100 hours. And second thing, it should be borne in mind, it gives expected output only when it is maintained at the nominal rated voltage or allowed to draw the rated current. So, this aspect has to be borne in mind. In fact, we will see when we take up various sources how varying conditions affect the life of a lamp. Life of a lamp would mean, one, it continuing to give the radiation output without any deterioration, and secondly, some of these things, I mean, it does not get. One simple thing is you are using an incandescent lamp. What is an incandescent lamp? It will get clear as we go along, but as the first thing is, it is an element working on the thermoluminescence. That means there is a filament which is heated. Now, we want that this filament is not destroyed. That is what I mean by maintaining itself. So, the thing is done by having what we call a photometric bench, and the test lamp along with the standard lamp or the laboratory standard lamp is compared, and the radiation from these two sources, what we call on an opaque screen called the photometric head, is observed. This will become clear and when we see the diagram. See, then what do we do? There are various ways of doing. One, the first and foremost simplest one is compare the test lamp with the standard lamp on the photometric bench simultaneously. One could be vary the position of the comparison lamp, okay, or the other could be varying the position of the test lamp. The third could be varying the position of the screen. Okay, we vary these. what are we looking at? We are looking at that on the photometric head, which is nothing but a opaque screen, the light radiation is of the same intensity. This is to be observed. So, what we see, we look at the brightness on the two sides of the screen and we look for equal brightness on either side. Okay. So, what are we doing? We are taking a standard lamp, we take the test lamp and a photometric head and we keep the screen between the two lamps and we observe the brightness on the screen or the photometric head due to these two lamps. Now, we can vary either standard lamp position or we can vary the position of the test lamp or the position of the screen for this condition, and obviously all this needs to be in a dark room. Of course, some of us have done some of these experiments using photometric benches in the school physics classes on light experiments. Here is a picture which shows the arrangement for photometric bench. So, the first method which we said is on a single bench simultaneously both the lamps are located and the photometric head is placed in between them. Let the distance between the source, standard source and the photometric bench be S, and that between the photometric head and the test lamp be T. Then one can say if the brightness is same on the screen at either end, on either side. Look, the brightness on this can be expressed using which law? The inverse square law of illumination, which says at any point x away from a source I, the illuminance is I by x squared. Applying that, we get Is over S squared is equal to It over T squared, and hence one gets It is equal to Is T squared by S squared. Needless to mention that photometric bench has a scale attached to it which enables us to clearly get the distance between the various between the sources and the photometric heads. So, this is a very important issue. And what are the various ways to balance? One, I keep the position of the head and the test lamp fixed. Vary the position of standard lamp, thereby I get the value. Alternatively, I keep the position of the standard lamp and the photometric head fixed, but vary the position of test lamp. A third way or yet another way of doing it could be keep the position of test lamp and standard lamp fixed, but move the photometric head and thereby get the value of S and T. That will give us the thing. There is another way of measuring is instead of using the photometric head, we use what we call the lux meter. Remember, when you are using a photometric head which is a opaque screen, it is somewhat subjective in the sense that it depends on the person who is involved in taking the brightness or in balancing. Once we use a meter which is being called illumination meter, which is marked in terms of what? Illuminance. Illuminance, we recall, was defined as the lumens per meter square or the light flux per unit area and is expressed in units of lux, hence the lux meter. So, what do we find? what we do on a photometric bench, we locate the standard lamp, and at a certain distance s, we get say a reading on the lux meter of x. So, what do? We take a photometric bench, we locate the meter at a distance s and observe the reading, let it be x. Then the next stage, what we do, we take the test lamp, we replace the standard lamp by test lamp, and then move or vary the position of the lux meter to obtain the same reading of illuminance. Here in the diagram, the distance marked x should have been capital T. So, once we do that, we have again knowing that illuminance is in terms of the given in terms of the luminous intensity and distance by the help of inverse square law. In the first case, we have Is by s squared equal to x, and in the second case we have It by t squared equal to x. Since we find the distance t between the test lamp and the meter for obtaining same illuminance x, then we get the luminous intensity of the test lamp as Is multiplied by t squared over s squared. So, to some extent, the subjectivity of using a photometric head is eliminated if we use a lux meter. The way to do is take the standard lamp, let us say it is placed on the photometric bench and the lux meter is positioned a distance s away from the standard lamp. And say it gives a reading x, then we relocate or replace standard lamp by the test lamp and move the meter till such time we read the same reading, and we get a new reading, new position of the meter away from the test lamp or the source of t. Then going by the law of inverse square law of illumination, one gets the luminance, the luminous intensity of the test lamp in terms of the standard lamp. This is a second way. There is yet another way is here, recall we just varied the distance. Instead of varying the distance, for the same reading of the lux meter, if I use a lux meter and position it at a certain distance x on the photometric bench from say a standard lamp and get a reading R1, and again on the same bench I replace the standard lamp by the test lamp and maintain the same distance x between the lamp and the meter, I get a new reading R2. Then what we get is that we can relate, in fact you remember that what are we reading in the lux meter? We are reading the illuminance. Illuminance is proportional to your luminous intensity. Recall inverse square law. In the first case, if the reading R1 was there, R1 is essentially Is by x squared. In the second case, we got the reading R2. R2 is It by x squared. So, since x is same, what do we have? We can say It equal to Is into reading with test lamp, which is R2, by reading with the standard lamp. So this is the way to go about making some measurements. This is fine as far as what goes as far as getting the luminous intensity. This is the first thing. Once we have luminous intensity, all other measurements or calculations become easy. In fact, that is why the photometry is an important issue for measuring. And how do we do it? We can do it by comparing with a laboratory standard. What's a laboratory standard? A laboratory standard is nothing but an incandescent lamp compared with a primary standard maintained in the standards laboratories and with the help of a photometric bench. We saw two ways of doing it, either using a photometric head or a lux meter. Now what you see is a way to create a simple lux meter. What we observe, there are two circles. Outer circle is a enclosed opaque sphere with a small opening, and the smaller circle inside represents the source. There is a diffusing screen so that most of the light flux goes through the opening and is measured using a photocell or illumination meter. We will look into the illumination meter or photocell, how it works, a little later. In a simple sense, it is a photoelectric device which sends an electric current on exposure to light, and this electric current measured is an index of the luminous intensity or illuminance, at the point where it is maintained. So this is how one could do. So this is another way of measuring. So this is not using a photometric bench. We talked about measuring the illuminance from a standard lamp, comparing and again maintaining at the same distance on a photometric bench for the test lamp and taking the ratio of the two readings. So you can, this particular arrangement is what we call photocell arrangement. So what you do, initially we keep a standard lamp at the center representing the smaller circle, observe the reading on the photocell, then replace it by the test lamp, repeat, and then you have the reading. The luminous intensity of the test lamp would essentially be luminous intensity of the standard lamp multiplied by R2 over R1. So this is how a photocell looks. So once again, recapping the standard units which we employ in the illumination thing. One of the fundamental thing is the radiation ability, which we define as luminous intensity, which is standardized as candela or abbreviated as CD. The next most important thing is total light output is the luminous flux, lumen. In fact, we will look at some of the things which are called as the light flux diagrams, because depending on the overall lamp system, although a lamp may be able to radiate uniform flux in all directions, depending on what we call the lamp shade, or in other words technically known as luminaire, it may direct the light and therefore it may change the light characteristics in the environment. So it becomes necessary to know the luminous flux or lumen. Illuminance, of course, is abbreviated as lux. Lx is known as lux, is the luminous intensity at a point, that is lumens per meter squared. Now there is another term called brightness, which we have also encountered earlier in talking about the functioning of the eye, is standardized as Lambert's. The difference between brightness and illuminance, though they look to be same is this: brightness is sort of the cause, illuminance is the effect. That is, if a light falls on a source, the effect of this light on that test object is what we call illuminance, whereas the light output available at a particular point, that is what we call the brightness. So, this, and here it becomes necessary for us to know some other units which have been in vogue, because though they are not currently used, but for the sake of completeness it must be taken care. They are in the FPS system, one may encounter when reading the literature, and in fact even we have encountered. One of them is foot candle, which is nothing but 1 lumen per square foot, which is essentially nothing but 10.76 lux. Or we do have another unit which is called phot. See, in fact the lux is a very large unit, so you talk in terms of phots, which is 1 lumen per cm square. Let us look at it this way: we are looking at the effect of a light over a certain unit area, and 1 meter squared is a very large area. So, if you look at the point effect variation, maybe sometimes if the variation is large over a certain region, it may be necessary for us to look over smaller areas. That is where phot becomes useful. It is 1 lumen per cm squared, or which is nothing but 10 kilo lux. And then you have Lambert. I told you Lambert is nothing but, again the brightness is talked about in terms of Lambert, it is 1 lumen per cm squared. If it is the illuminance, we would use the term phot, and for brightness we would use Lambert. 1 foot Lambert is nothing but 1 lumen per square foot. So, the foot candle would be the cause or the response due to a certain source. Foot Lambert would talk about the brightness of the thing. See, there are two things. Sometimes the walls have some brightness based on the natural light, that is expressed in terms of this. So, going a little more into brightness, because brightness and illuminance confuses oftentimes, and it is necessary for us to know the difference. By definition, brightness, or in fact brightness is also known as luminous, whereas the effect we call in terms of illuminance. Luminous intensity of any surface in a given direction per unit of the projected area of the surface as viewed from that direction. This is very important in interpreting the light flux diagrams of the sources. So, now it is time to look at the photovoltaic cell. I talked to you about that there is a photovoltaic cell. We have what is it called the it uses the photoelectric effect. As can be seen, there are 3 layers. It appears to be 3 layers, but it essentially there is a small thin semiconducting layer S, a small gap on top of which a transparent thin metallic layer M is placed. This gap is talked about as the barrier, and this transparent layer on which the light is incident, and as can be seen, there is a region marked R, which is nothing but the covered thing, that is only it is coated with some metallic this thing. Now, what do we do if supposing this is transparent? On exposure to light, the semiconductor gives rise to certain electrons, and there is a current flow between the 2 layers. Now, this current is collected and read on this ammeter shown. So, this acts as a photovoltaic cell or the lux meter. This is the principle of the lux meter. Now, how the ring is located will become clear as we go along. So, the first thing is there is a sensitive element which is a semiconductor which gives rise to electrons or goes into conduction mode on exposure to light. The two materials that have been found suitable for this particular application have been selenium and cuprous oxide. These are the semiconductor materials. There is a small, that means what is done? Look at the diagram once again. We have a small steel plate. In fact, if you want to collect this current which is generated, you need to have electrodes. That is why that on a small steel plate, you thin layer of selenium, let us say the selenium and cuprous oxide both are possible, let us call it, we are using selenium, and it is placed. Then in turn we coat it with a thin film of metal, and there is a collection ring of metal. See, the first coating M is transparent, whereas the outer ring is not transparent. Okay. So, this is how it looks. One could see the top view. The R is opaque, whereas M is transparent. This is the top view, and that is how the current is collected between P and R. B is the barrier. On exposure to light, light enters through M, releases electrons from selenium. They cross the barrier to B to M and are collected through R and P. Now, once the current is allowed to flow, this current is indicated in the ammeter, which could be a microammeter, and this gives the calibrated in lumens or lux. So, that is the principle behind the photoelectric cell. This is very important. Now, from the measurement point of view or use point of view, one other thing which becomes necessary is the light flux distribution curves that are provided by the manufacturers, and they are often guided by the accessories that are used with the lamps. Now, as we study the sources, you will get clear, like incandescent lamp is placed in a glass envelope which is called a bulb. We know it as a bulb. The glass envelope is there. Now, we have seen lamps which are coated inside on the top, so that most of the light flux is radiated downwards. So, that is in a simple sense a mechanism to direct the light or control the light. Now, the whole, that could be one way of directing the light. The other thing that happens is often we place these lights in what are called lamp shades, which are again coated with reflecting material which reflects bulk of the light going there, and therefore these accessories which control or direct the light are called luminaires. And we have also talked about one phenomena that happens with the sources as far as eyes go is the phenomena of glare. Whenever eyes are in the straight line with the intense light coming from a source, there is a phenomena of glare. Now, to avoid this, it's oftentimes light is diffused. So, the whole scheme of reflecting, controlling the light to be directed in a particular direction and diffusing are called luminaires. So, let us see what luminaires are, how their distribution curves are, and how do we make the estimates. In fact, this also forms a part of photometry, though it may not be exact measurement, but it is necessary to understand how to. Okay. So, you have luminaires which are basically directing the light from the source. Now, as I told you, to avoid glare you may be using diffusers, and this could be in terms of one common thing which we have seen for ornamental lighting is to use spherical diffusers, which are also called, because it resembles the Mother Earth, as globe. They could be refracting reflectors. Now, depending on the type of application, you could have wall brackets, and street lights we have seen, they are so positioned that the street users or the vehicular traffic is able to use. So, therefore, all these have what are called light distribution curves in the various planes, which is nothing but the luminous intensity vis-a-vis angle of emission. We have both horizontal plane and the vertical plane passing through the center. Okay. So, now this is a typical light distribution curve. What we have is you could call it as a vertical. Assume that there is a lamp along with its luminaire, that is, if the lamp is already pre-coated inside, that itself would be reflecting. So, considering all that, at various angles how the light flux distribution is, it is talked in terms of luminous intensity per unit area. So, we have such curves given. So, whenever we buy a complete lamp system, we are provided with such curves. Now, for me to be able to assess the requirement of lighting in a particular room, I may need to use these curves together and be able to arrive at the luminous intensity or illuminance on the work table, depending on the nature of the work. Work table, when I mean, it not necessarily table, work plane is what I mean here. So, in fact, there is one particular way we have talked about, and we talk about point source. We said the total flux is talked in terms of mean spherical luminous intensity called lumens. One has to arrive at that. When normal naked lamp, it is nothing but if ICD is located at the center, one gets I by 4 pi as the MSLI, because it is uniformly distributed in all directions. But observe, when it is given in this kind of a direction, the light intensity is not same in all directions, and that is taken care by considering the polar curve provided. Like here, we have a polar curve given for a lamp marked curve A. Incidentally, the lamp is placed at the point O, and the curve takes the shape of a heart. So, now in order to get the mean spherical luminous intensity, what we do is we construct what is called as a Roseau diagram. How do we go about? We start, take the polar curve A given, take O as the center of the lamp, then take any convenient radius, okay, and here the most convenient radius would be my polar curve is extending up to OC. So, I take that as the radius and draw a semicircle, and then from O at several points I keep drawing radial segments to the polar curve, which means initially when I go upwards, originating at O, it meets at O itself. Then I relate, that is the intensity value, I relate that and take the projection onto another vertical line marked DE. Let us say I take a radial going upwards at O, whose length is 0. Then I project it as from B onto D of 0 length horizontal, that is the intensity. Now, let us say the second radial meets at P, and which is marked as at P prime on the line DE of length P prime P double prime, that is the radial distance from O to P on the polar curve. Similarly, at another radial we are seeing cuts the polar curve at Q. This maps say at Q prime on the line DE. Q prime, Q double prime gives the luminous intensity corresponding to that angle. So, this is how, supposing you are positioned there, this is the luminous intensity in the direction. So, basically by having a luminaire and a director, selectively you are adjusting the luminous intensity in various directions, whereas in a normal simple source it is same in all directions. Now, we see the radial which cuts at R maps as R prime, R double prime, and similarly S prime, S double prime. So, we get the number of this thing, the average of these horizontal lines like EF, S prime, S double prime, R double prime, Q double prime, P double prime would be the mean spherical luminous intensity, or in other words, the area of this curve is an index of mean spherical luminous intensity. The construction of this diagram from the polar curve is what we call Rossum diagram. So, for any given lamp with the lighting system, we have a polar curve given in a particular plane depending on the plane of interest. If you are looking at a work table, you need to know the horizontal polar curve to be able to get. But if you are looking at a lamp for application on the streets, you need a vertical plane. So, that is how it is done. So, the luminaire is the one which distributes or creates these polar curves, which can be whose effect can be taken care through Rossum diagram. And what do the luminaires do? They support and also bring electrical connections to the lamp. Remember, all sources are being fed by electrical energy. They in fact control and direct the light and distribute as required. And there is an additional responsibility on the whole system, that you have to keep the temperature within the prescribed limits. See, if our illumination system tries to go raise the temperature, it is going to be a burden on the air conditioning system, especially in the interior lighting. Now, we already said brightness could be measured using an illumination meter, which is activated by a photoelectric cell, and we have seen how a photoelectric cell is nothing but a layer of semiconducting layer and a conducting transparent layer which generates electric current upon exposure to light. Now, brightness or luminance is the luminous intensity in the direction of interest, but for the unit projected area. This is very important, and we have already said we use the Rossum diagram to get the mean spherical luminous intensity. This becomes very important because unless you have an idea of this, it may not be possible for you to arrive at the number of sources, location of the sources, etc. So, this apart, one looks at that these luminaires should be very easy to install and maintain. At the same time, you have to have a pleasing appearance. We said right in the beginning of this course that illumination engineer has to have aesthetic sense just as an architect, and in fact light is or illumination is provided so that object of interest is visible or perceivable, but not the source itself, unless it is the ornament of observation, and it should have be very pleasing appearance and be very cost effective. Requirement for good luminaires can be therefore listed as they should provide good support and electrical connection to the lamp, of course depending on the voltage of operation, and in fact though I say it should control, direct and distribute as required, it's in order to say that these days there are electrical controls available which are part of the luminaire and keeping the temperatures within the prescribed limits. They should be easy to install and maintain. Maintenance is one important aspect that takes away a lot of our time and money. Then in order to focus or get the required kind of radiation in a direction, lenses and prisms are often used, and some factors which are necessary in order to evaluate, there are one major factor is what we call depreciation, or known as maintenance factor. In fact, depending on the type of maintenance possible or carried out, we can say that if the virgin lamp has a certain light flux radiation capability, it reduces with time, and this even for best of the lamps is around 0.85, which can be as low as 0.6. Then the other thing which is often kept in mind is minimum illuminance should never be less than 70% of the maximum value. In fact, if you see guidelines, which are one of the good source for getting guidelines, is Illumination Engineering Society books, which talk of average level, but we need to have reasonably uniform illuminance. It cannot be abruptly changing, that will cause fatigue on our eyes. Therefore, it should be assured that you have the nowhere in the work area it's less than 70%, and this in fact has been found that is achievable if you have multiple lamps by keeping a 1 to 1.5 ratio between spacing to height on the work plane when you have to use multiple, and this applies for point sources, not for line sources. And of course, brightness, luminance, we know we have already defined is the luminance. Now this apart, there is yet another factor called utilization factor. Depending on the type of lamp we have, there are different kinds of utilization factor, which means out of the total light that's available, how much of it is getting used. See, there are these days you have luminaires available where 0.9 to 0.95 of the light is directed, but the conventional open lamp shades only about 0.4 comes down onto the object, and there are certain open pendant things where very little light comes out. In fact, in trying to avoid glare, I said we use diffusers, and that's where some amount of light is always lost. These have to be okay. So the lecture summary therefore could be: light output from a source of light is obtained by comparing with a primary standard or a standard lamp. Now how do we do that? I said it is using by comparing with a laboratory standard on a photometric bench, where a photo head is used. A photo head is nothing but an opaque screen, and this type of measurement is subjective in nature. Methods of comparing a test lamp with the standard lamp: vary the position of standard lamp, number one. So what do? You keep the photometric head and the test lamp fixed. The second thing could be keep the standard lamp and the photometric head fixed, vary the test lamp. Now to avoid the subjectivity, we talk of using what we call the lux meters, and wherein we could take the test lamp and the lux meter at a fixed distance, and standard lamp and lux meter at a fixed distance, get the two readings. The ratio of the two readings gives the test lamp luminous intensity. Here again you could either fix the distance or fix the reading of the lux meter, accordingly get. Now luminaires are invariably employed. In fact, nowhere we use the lamp directly. Any lamp we use is with its accessories. Luminaire is a term used for the complete accessories that are used, which will consist of your reflectors, control gear, other accessories, and remembering that it's driven by electrical energy, the lead-ins, lead-outs all together, and so they direct the light in the desired direction. They could be direct reflectors or diffusing. I said unless the light comes reflected from ceiling, say for interior lighting, if the light rays are in the line of vision, they can cause glare when the intensity is high. This has to be avoided. This could be done easily using diffusers. Therefore, you have luminaires, which are directed reflectors, diffusing, and they could be using prisms or various kinds of things. So, we could have some questions based on this lecture. Why can't an incandescent lamp be used as a standard lamp? However, I said incandescent lamp is used for comparison methods in the laboratory on a comparison with the thing, keeping in mind that we maintain the voltage and wattage. What is the utilization factor? What is maintenance factor of a luminaire? What are the advantages of diffusing type of a luminaire? Now, some of the answers to questions in the previous lecture, they are: what is the standard unit of luminous intensity? The answer is candela. Remember, the standard unit of luminous intensity has been adapted based on the origin of primary standard. In fact, primary standard has originated through several levels. Began with the first and foremost standard was wax candle. Then what is MSLI? MSLI is the mean spherical luminous intensity, is the light flux radially outward from a source, which may be assumed to be a point. In fact, that is why when we are dealing with the lamps, we look at their light distribution curves, we saw that, and how one gets the mean spherical luminous intensity through a process of constructing the Roseau diagram. What is the standard procedure to measure luminosity? The luminosity can be measured by standard procedure of photometry. That is what we saw in today's lecture. Thank you.